Welcome back, and in this video I want to step through how DNSSEC works inside a zone, specifically how it allows a DNSSEC resolver or client to validate any resource records within a zone. This video is focusing on the data integrity part of DNSSEC, and coming up after this is another video where I'll cover the chain of trust and origin authentication benefits which DNSSEC provides in a lot more detail. Now, because this video covers digital signing within DNSSEC, it's important that you've watched my previous videos on DNS, on hashing, and on digital signing. If you haven't, all of those videos will be linked in the description. If you have, then let's jump in and get started. Now, to understand DNSSEC, I first need to introduce a term, and that's a resource record set, or RR set. Let's look visually at what this is. We'll start with a DNS zone of ican.org, and I'm using this as an example in this lesson as it's one which I know to be DNSSEC enabled. Now, inside this zone we have a number of resource records. First, www.ican.org, which is a CNAME record, and remember, CNAMEs point at other records, and in this case it points at two other records. One of them is an A record, so IP version 4, and the other is an AAAA record, which is IP version 6. Now finally, we have 4 MX records for the domain, pointing at 4 different mail exchange servers. Now, each of these are resource records. I'm showing a total of 7. So what's a resource record set? Well, a resource record set, or RR set, is any records of the same name and the same type. So in the case of the left 3, this means each of them is their own RR set. But in the case of the MX records, they all have the same name, so ican.org, and they're all MX records. And this means that all 4 of these are inside one RR set. RR sets are just sets of resource records. They make it easier to deal with records in groups versus single records, and in the case of DNSSEC, it keeps things manageable in other ways, but more on that in a second. Now, this is what an RR set might look like if you actually interact with DNS. Notice how all the names are the same and all the types are the same. So why do you need to know this? Well, because RR sets are used within DNSSEC. Right now, there's no way to tell if any of these resource records are valid. DNSSEC provides this functionality, but it's not individual resource records which are validated by DNSSEC. It's resource record sets, or RR sets. Now let's take a look at how this works. So DNS allows us to validate data integrity of record sets within DNS. It doesn't work on individual records, rather it works on sets of records, RR sets. Let's take a look at how. So we start with the same ican.org zone, and inside here I'm going to step through one RR set example, the set of 4 resource records which make up the MX RR set. Right now, without DNSSEC, if a bad actor found a way to change or make you think that these records had changed, then email delivery could, in theory, be redirected. DNSSEC helps prevent that using 2 features. First, we have RRSig, which stores a digital signature of an RR set using public and private pairs of keys. This one key pair is known as the Zone Signing Key, or ZSK. The private part of this key pair is sensitive, and it's not actually stored within the zone. It's kept offline, it's kept separated, but you need to know that it exists. Like any private key, you need to keep this key safe and not accessible from the public domain. So once again, an RRSig contains a digital signature of an RR set. So we take the RR set, which is plain text, we run it through a signing process. Let's call this the Digital Signaturatron 9000. In reality, it's just a standard cryptographic process. This process uses the private part of the ZSK to create a signature, and this is why it's important to keep the private part of this key safe. This output, the signature, can be stored alongside the plaintext RR set in the zone using the same name, but the record type is RRSIG. Any normal DNS clients will only see the RR set. Any DNSSEC clients will see the RR set and the corresponding RRSIG. Now this uses digital signing and hashing. If the RR set changes, the RRSIG has to be regenerated in order to be valid. If the RR set changes without a corresponding change to the RRSIG, the result is an invalid signature, and so you can tell if anything has changed without the approval of the person controlling the private zone signing key. And this is because only the private part of the zone signing key can be used to sign RR sets, creating an RRSIG. Assuming that you trust that the private zone signing key is in safe hands, then you know that if there's a valid RRSIG for a corresponding RR set, that RR set is in a valid state created by the zone admin, and if it changes, you can tell. Now the important question is, how can a DNS client or resolver verify the RRSIG? For that, there's another piece to the DNSSEC puzzle. We need the public part of the zone signing key to be able to verify signatures or RRSIGs created using the private part. Lucky for us, public parts of the key pairs aren't sensitive and don't need to be guarded. We just need a way to make them available. So consider this scenario. We have the same ican.org domain. We also have a DNSSEC resolver here at the bottom. How do we know it's a DNSSEC resolver? You'll just have to trust me, but it is a super smart resolver. Now inside the zone we have the MX RR set for the ican.org zone. We also have the MX RRSIG, which remember is a signature of the RR set, created using the private part of the zone signing key. Inside a DNSSEC enabled zone you'll find another record, the DNS key record. The DNS key record stores public keys. These public keys can be used to verify any RRSIGs in the zone. DNS key records can store the public key for the zone signing key, so the ZSK, and also a different type of key, the key signing key or KSK, but more on this in a second. We're going to do this step by step. This is what a DNS key record might look like, and because it can store different public keys, there's a flag value. A value of 256 means that it's a zone signing key, and a value of 257 means it's a key signing key. So the top one here, this is the zone signing key. And it's this value which is the last piece of the puzzle. It means the DNS resolver can take the RR set, which remember is the plaintext part, and using this together with the matching RRSIG and the DNS key record, it can verify that both the RRSIG matches the RR set and the signature was generated using the private part of the zone signing key. And the result of this is that our DNSSEC capable resolver at the bottom can verify the RR set is valid and hasn't been compromised. Now this is all assuming, and this is a big assumption, that we trust the DNS key, specifically the zone signing key. You have to trust that only the zone admin has the private part of the key, and you also have to trust that it's the correct zone signing key. If you do, you can trust the RRSIG and matching RR set are valid. Now a real-world comparison of this would be to imagine if somebody shows you an ID card which has their photo on it. The photo ID only proves their identity if you trust the photo ID is real and it was created by a genuine authority entity. In humans, this trust is a bit vague. That's why fake IDs are such a problem. This isn't a problem with DNSSEC, because as you'll see, we have a chain of verifiable trust all the way to the DNS root. The DNS key record also requires a signature, And this means a matching RRSIG record to validate that it hasn't been changed. The DNS key records, though, these are signed with a different key, the key signing key, or KSK. So as the name suggests, this key isn't used for signing anything in the zone, instead it's used for signing keys. So the zone signing key is used for signing everything in a zone, so to create most RRSIG records, except the DNS key records. These are signed by the key signing key, creating the DNS key RRSIG record. Now I get it, I've just introduced another type of key, so let's look at how this all fits together within a DNS zone. At this point I want to cover two really important points about DNSSEC. First, how does a key signing key fit into all this and why do we have them? And second, what mechanism allows us to trust a zone? We know that RRSIG records let DNSSEC resolvers verify record sets, but how do we know the keys used within a zone themselves can be trusted? To illustrate both of these, let's start with the same ican.org zone, and then off to the right side a related area but containing more sensitive things. This might be a physical key store like a filesafe or a HSM device. Contained in here to start with is the private zone signing key, and this is used together with an RRSet record to create a corresponding RRSIG record. Then the public part of this zone signing key is stored in the DNS key record. The flag of 256 tells us that it's a zone signing key. At this point I want to pause and take a quick detour. If this was all that we had, so the DNS key, we couldn't trust it. Somebody could swap out the DNS key record, putting a new public key in there, use the private part of that fake key to regenerate a fake RRSIG, adjust the RRSet and take over email for this domain. We need a way of ensuring the zone signing key is trusted. If we didn't have some kind of trust chain, we would need to manually trust every zone within DNS, and that would defeat the purpose of having a globally distributed system. So, the way that this works is that this zone, so ican.org, is linked cryptographically to the parent zone, which is .org. So just like with normal DNS where name server records are used in the org zone to delegate to domains such as ican.org, the org parent zone also has a way to explicitly state that we can trust ican.org as a zone, and I'll talk about exactly how this works in the next video. For now, I want to focus on this zone. Now if we used a single key, so just the zone signing key, that would work, but this would mean if we ever wanted to change the zone signing key, then we would have to involve the .org parent zone. Best practice is that we want to be cycling keys fairly often, and doing that where it also requires updates up the chain would become inefficient. And so we have this new key pair, the key signing key, or KSK. Now there's a private part and a public part. The private part is used to sign DNS key record sets, which creates an RRSIG of the DNS key. And this makes it easy to change the zone signing key used for a zone. We just have to regenerate all of the RRSIG records, update the DNS key record set, and then regenerate the RRSIG of the DNS key record set using the private key signing key. All of this is inside our zone only. It doesn't involve the parent zone in any way. We store the public part of the key signing key in the DNS key record set. But now we have a new problem. How can we trust the key signing key? Well, spoiler, it's referenced from the parent zone, in this case .org. So remember how I said that the DNS key record set stored both zone signing and key signing public keys? Well, this is the main point of trust for the zone. This is how trust is conveyed into the zone. Because the parent zone links to the public key signing key of our zone, assuming we can trust the .org parent zone, because it references our zone's key signing key, we can trust our zone's key signing key. This key signing key signs our zone signing key, and the zone signing key signs all of the RR sets to create RR SIGs. We have a chain of trust created between two different layers of DNS, specifically DNSSEC. Now we're at the point now where you should understand how DNSSEC validates things within a single zone, how it uses RR SIGs to validate RR sets, how it uses the DNS key records to get the public keys to do that validation using the zone signing key, how a key signing key is used to create an RR SIG of the DNS key which allows the validation of that DNS key record, and how the parent domain or parent zone trusts the public key signing key of the child domain or zone. Now you don't know how this trust occurs yet, that's something I'm going to be talking about in the next video. I've also stepped through why two different keys are needed, using a zone signing key for signing within a zone and a key signing key for signing that key. That allows an admin split. The key signing key can be referenced from the parent zone, while the zone signing key is used exclusively within the zone, and this means that a zone signing key can be changed without requiring any changes to the parent zone. So what position does that put us in? With this functionality using DNSSEC, what have we gained in the way of additional security? Well, we can now verify the integrity of data within this specific DNS zone. So we've eliminated the DNS cache poisoning example, assuming we trust the key signing key and also assuming the key signing key hasn't been changed as part of an exploit, then we can trust all of the information contained within a zone. Now in the next video, I'm going to step you through exactly how DNSSEC creates this chain of trust. And this allows a parent zone to indicate that it trusts the key signing key used within a child zone. And this same architecture at every level of DNSSEC means that we can create this entire end-to-end chain of trust which can be verified cryptographically. Now at this point, that's all I wanted to cover in this video. In the next video, I'm going to step through how this trust from a parent zone to a child zone is handled within the DNSSEC hierarchy. And we'll go through how the query flow works step by step. For now though, go ahead and complete this video, and when you're ready, I'll look forward to you joining me in the next.